Populations. Here we go. First up, reminder of where we're at in the list of things that we did in our very first notes, where you listed all the different levels. We're looking just at populations today. We're going to have another days for all the other ones. A population is a group of the same organisms living in the same place, and they are capable of breeding together and making babies. Whether they choose to or not is something different, but they're capable of it. Sorry about that. So in that picture on the left side, we have a population of zebra and a population of whatever those plants are. On the right side there, that is a population of snails. So it's a group of the same things, same place. When we're talking about populations, we can count them, but it's kind of hard because there's probably a lot of them spread out over a lot of area. But there are different factors that would affect how many are in there. First off, the number of births. Second, number of deaths. Third, immigration, which means moving in. Fourth is emigration, which means moving out. So for example, if you moved to the United States from, let's say, Mexico, you immigrated with the I to the United States, you emigrated with the E from Mexico. If births or immigration are higher, that means the population numbers are going to go up. There's more. If deaths or emigration are higher, that means the population is going to go down. There are math equations you can do. We're not going to get that in depth. In real life, it's hard to count how many living things there are in any one area. The overall number, or the approximate number, our guessed number of individuals in that group are the population density. There are some organisms that have a very high population density, and there are some that have lower population density, and then there's ones that are in the middle. For example, on the left, all of those are caribou, which are large animals that are sort of like deer, and they just walk across Canada eating all the plants. There can be millions of them altogether. That would be high population density. On the right picture, we have low population density, which is usually what you see with predators. For example, like cheetahs, there's usually just one or maybe a mother and her cubs, but there's not a big group of them like you'd see with the other ones, which kind of makes sense for a predator. You wouldn't want a whole bunch of other cats trying to take your food. The caribou don't have that problem. They can just walk to another place and eat more plants. When we graph that population over time, it can do one of two things. It can look like this, or it can look like that. Exponential growth means that the population is growing constantly. It's if in math class, if you were to graph an exponent, that's what it would look like. It looks kind of like the letter J. It is going up and up and up and up and up and never stopping. This only happens when the conditions are absolutely perfect. So that means no predators, no competition, no disease, or at least not any disease that's really slowing them down. Lots of space, lots of food, lots of resources. There are some living things that will have this kind of growth for a little bit, but not all the time. The only living thing on Earth that has had this population kind of growth forever is humans. Here is an example for humans. We're getting pretty close to 8 billion. Notice the time scale over here is in billions. We have an exponential growth curve. Most populations are not going to be able to just keep growing forever. They're going to run out of food or space, too much competition, there's not enough mates. So something is going to cause them to slow down. When that happens, you make an S-shaped graph, which kind of looks like this, S shape. That is called a logistic growth graph because it grows really fast and then slows down or stops because something limits it. Something slows them down. So growing fast, stop. S-shaped. If you were to graph a logarithm, that's what it would look like. That's where the name came from. We're not doing the exponent or logistic math. I'm just telling you, like, if you were to look at it in math class, that's what it would look like, and that's where the name comes from. That top number whatever that number is at, is called its carrying capacity. That's the highest number that an environment can support. So for this example, these paramecium living in a petri dish, their carrying capacity is about 200. In real life, it might be 202 or 195, but it's somewhere around 200. Do note, though, that carrying capacity is different for different living things in different environments. So the carrying capacity for caribou in Canada is going to be different than the carrying capacity for, let's say, wolves in Canada. Or it's going to be different for cheetahs in Africa. Or it's going to be different for squirrels in Pennsylvania. Every carrying capacity is going to be different. There's some number that they kind of stop around. Important thing to note that populations can overshoot their carrying capacity. The only ones that keep overshooting it and never come back down so far has been humans. But, for everybody who's not a human, you can overshoot it, but you come back down eventually. So, for example, things like deer, rabbits, birds, in the spring, they have a whole bunch of babies. There's a really high population increase. But then as fall and winter happen, they run out of food, there's diseases, they get hit by cars, they maybe get hunted, maybe it's too cold for them to survive, other predators are eating them, so eventually they come back down. Even if they went way high, they come back down eventually. What can limit a population's growth? Limiting factors. They're factors that limit the growth. There's two kinds for your notes. First up is density dependent. This means it depends on the population size. If there's more of you, it's going to impact you more. This includes competition. There's more of you using less things. There's going to be a fight. Predators. There's more of you to eat. Predators are going to come after you more. Diseases and parasites. Think of like a sickness within an elementary school. If you have one group of little kids, one of them gets sick, the whole group's going to get sick. It's like that. The bigger the group, the more the disease is going to pass on. Density independent factors affect everybody equally. It doesn't matter if you're a human or a squirrel or a worm, you're going to get impacted equally. Something like if a tornado hit Lebanon, it doesn't matter who you are, it's going to impact you. So extreme weather, tornadoes, hurricanes, natural disasters like earthquakes, volcanoes, tsunamis, meteors hitting, and human impacts. If you cut down an entire forest and build a Walmart on top of it, well, everybody who lived in that forest is affected. Whether they were a tree or a deer, they're getting impacted. But one more time, density dependent affects you more if there are more of you. Density independent affects everybody all the same. Got it? There is no secret word for today, but thanks for listening. Maybe you'll still get a bonus point if you answered that last question correctly. That's it for now. See you next time around.